KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we start with conservation of angular momentum. Okay, in this chapter, rotational motion. When compared in our previous class, we focused on angular momentum in case of rotation about a fixed axis. So in this class, we start with rotational motion. Okay, rotational motion, and in that conservation of angular momentum. Okay, right. See here, ma. So conservation of angular momentum we already discussed in the same chapter, but now we are going to discuss the same thing along with the applications to daily life. So in our daily life, where we come across this conservation of angular momentum and what will happen. So if you apply this conservation of angular momentum to one particular situation, what we come across in our daily life, what happens to the moment of inertia and what happens to the angular speed, right? That is our discussion here. See this, basically, so what is conservation of angular momentum? If the external torque is 0, regarding rotational motion of a body or a particle about an axis of rotation, about one particular axis of rotation, if you take the rotational motion of a body, when the external torque is 0, its angular momentum, right? Its angular momentum is constant. L is equal to I omega. That only I have written here. From our previous discussion, if the external torque is 0, Lz is equal to I omega, that is equal to constant. Okay. See this, for symmetric bodies, this is the expression we got in our previous class. Okay, this is the expression we got in our previous class. That is what is Lz and what is L perpendicular. Okay, this is the expression we got in our previous class, but here we are saying that the Lz can be replaced. For symmetric bodies, Lz may be replaced by L. So in this law of conservation of angular momentum, what I am saying is, from our previous discussion, if the external torque regarding the body which is in rotational motion is 0, then we can write L is equal to I omega is equal to constant. Here the Lz is replaced with L. That only he is saying, for symmetric bodies, Lz may be replaced by L. Okay, next, we can experience many examples from our daily life regarding law of conservation of angular momentum. Now we are taking one example to discuss the law of conservation of angular momentum. What is the example? A girl is sitting in a chair. That chair is able to get rotational motion. In barber shops you can see some chairs. So that chair will rotate. You need not to rotate, but the chair will rotate. Okay. So the type of chair, in that type of chair, a girl is sitting and she is stretching her hands. She is stretching her hands. This is the picture. So it is one of the example which happens in our daily life. Here we are going to discuss the law of conservation of angular momentum. Otherwise, simply conservation of angular momentum. So the concept of conservation of angular momentum we are going to discuss in this example. See here, he is saying like this: sit in a swivel chair. Sit in a swivel chair with your arms folded and feet not resting on the ground. Okay, that is what, if you observe carefully, it is the chair ma. These feet of the girl not resting on the ground, so on the chair, so she wholly can rotate. Okay, that is the situation regarding her. Now she asked her friend to rotate the chair. So when the chair is rotating rapidly, okay, so while the chair is rotating with considerable angular speed, suppose if you stretch her arms, if she stretch her arms, then angular speed will be decreased. Angular speed will be decreased. This is the important point we have to notice. So what is the important point? When the girl is rotating in a chair, with considerable angular speed, suppose if she stretch her hands, what will happen? If she stretch her hands, angular speed is reduced. Okay, right. Suppose if she close her hands, I think you know what is stretching of hands and what is the closing of hands, right? Suppose if she close her hands, what will happen? She has to experience the opposite effect. What is the opposite effect? Angular speed will be increased. Here the point is, just by sitting in a rotatable chair, by stretching her hands, by closing her hands, she can increase the angular speed and she can decrease the angular speed. By stretching her arms, she can increase the angular speed. By stretching her hands, the angular speed will be reduced. By closing the hands, the angular speed will be increased. Opposite effect. Right? This is the situation where the principle of conservation of angular momentum is applicable. Okay? See here. If friction in the rotational mechanism is neglected, there is no external torque about the axis of rotation of the chair, and hence I omega is constant. You just keep in mind, ma. So when he is saying that there is no external torque, you know tau is constant, no? So when there is no external torque, you know tau is 0. When tau is 0, okay, then what happens? L is equal to I omega, no? So I omega is constant. So when I omega is constant, stretching the arms increases I about the axis of rotation, resulting in decreasing the angular speed. You know very well, when I omega is constant, I is inversely proportional to omega. So if I increases, omega decreases. If I decreases, omega will increase. So that only he is saying here, you know, by stretching her arms, I will be increases I about the axis of rotation, resulting in decreasing the angular speed. Right? Bringing the arms closer to the body has the opposite effect. So what is the opposite effects? I will be decreases and omega will be increased. Right? And you know the formula I is equal to mr square. So when she is stretching her arms, you know the R value will be increased so that I will be increased. So you can say, I am saying some other point, I am saying the cause why the I is going to increase. But according to this formula, when I will be increased, omega should be decreased. So that only is happening. See here, So stretching the arms increases I about the axis of rotation, resulting in decreasing the angular speed omega. Bringing the arms closer to the body has the opposite effect. Opposite effect means what? Decreasing I and increasing angular speed. Okay, right. So this is the main concept. Throughout this discussion, what I am saying here related to conservation of angular momentum, the key points are only two things. One is, when she stretched her arms, angular speed is reduced. So there itself, moment of inertia will be increases. That is one point. Second point is, when she bring the arms closer to the body, right, angular speed will be increased, and moment of inertia will be decreased. These 2 points are very important throughout this discussion, conservation of angular momentum. So by keeping these points in our minds, we can go for many examples. For example, see here, a circus acrobat and a diver take advantage of this principle. You know who is the diver? So when we are going for swimming in well and pond, right? So we are going to dive, right? So when you are going to dive, we are taking the advantage of this principle. That is what law of conservation of angular momentum. Okay. Not only this, also skaters and classical Indian skaters, skating, and classical Indian or Western, classical Indian, that is what Kathakali, Kuchipudi, like that something are there, no? So dance, classical Indian or Western dancers performing a pirouette on the toes of one foot display mastery, right? Display mastery over this principle. So that is what happening. This is not only in pubs, right? And in some of the circuses and in some of the dance shows, there is a pole, right? Just around the pole they will dance. Okay, this is possible just by understanding the law of conservation of angular momentum. They have that ability naturally, they have that ability by practice. It is not matter, I am not talking about that, but how it is possible from physics point of view, from rotational motion point of view, from conservation of angular momentum point of view, right? That's why I want to ask you to check and to observe. Okay, right. Now we are going to discuss rolling motion. Okay. So this is what when I am taking rolling motion, we have experienced many times. Okay. Suppose for example, if you see the general stores, there the oil drums, they are going to take from one place to another place just by rolling. Okay. Right. Here, if you observe carefully, this is what acrobat, right? One acrobat employing the principle of conservation of angular momentum in her performance. See here. This is what he is getting that he is getting the advantage of principle of conservation of angular momentum. Okay. Right. When he is performing that stunt or something. Okay, see here, now we are going to discuss about rolling motion. It is very common motion. If you observe carefully, all wheels used in transportation have rolling motion. Okay, but we have to observe that, and here our discussion of rolling motion begin with the case of disc. You know what is disc? Okay, but the result will apply to any rolling body rolling on a level surface. For example, you can take the cycle wheel, so which is also in rolling motion on the level surface. That also you can take as example to study or to understand or to discuss the rolling motion, right? So here we have to assume that the disc rolls without slipping. I think you understood what is meant by slipping, right? Suppose sometimes on rainy day, if you press the cycle brake suddenly, right, brake will not, cycle will not stop and it continues to move in like skidding, not rolling. So that is not our discussion. Here to discuss this topic rolling motion, our discussion is pure rolling motion. So rolling without skidding, rolling without slipping. Okay, sometimes we are calling it as skidding also. So what does it mean? At any instant of time, the bottom of the disc which is in contact with the surface is at rest. Is at rest on the surface. So at any instant of time, the bottom of the disc which is in contact with the surface is at rest on the surface, right? So here we are going to discuss about pure rolling motion. So we should not consider the motion rolling with slipping. So we have to consider only pure rolling motion. If you take pure rolling motion, we have to say that at any instant of time, the bottom of the disc, for example, if you take disc as an example to discuss the rolling motion, the bottom of the disc which is in contact with the surface is at rest on the surface. Okay, right. And we also discussed in our previous classes of the same chapter, rolling motion is a combination of rotation and translation. Okay, that we discussed in our previous classes. And we also know that translational motion of a system of particles is the motion of its center of mass. So in the same chapter starting topic, I told you what is center of mass, how to calculate the position of center of mass, how to calculate the velocity of center of mass, acceleration of center of mass, right? So generally when we talk about translatory motion of one particular object, we are observing only the center of mass, the motion of center of mass. That's what he is saying here. Okay, right. Now we start to discuss how the object is in rolling motion and what are the factors. Okay, this and all we have to discuss, right? See here first, see this picture, observe carefully what's happening in this picture. Here what I am saying is, let VCM be the velocity of center of mass. Velocity of center of mass. Let VCM be the velocity of center of mass, and therefore the translational velocity of the disk. Okay. So just now I told you before 1 minute. So we know that the translational motion of a system of particles is the motion of center of mass. No, that's we already discussed in the same chapter, the starting of this chapter. Okay. So here what I am saying is, so based on that sentence, let VCM be the velocity of the center of mass, and therefore the translational velocity of the disk is, okay, when VCM be the velocity of center of mass, and therefore you can say that VCM is also the translational velocity of the disk. Okay. So he is also saying, since the center of mass of the rolling disk is at its geometric center. So regarding the regular bodies, where is the center of mass? That is the topic we discussed with the help of table. So I think before 5-6 classes we discussed one table there for many regular bodies. For many regular bodies we discussed where is the position of center of mass with respect to different axes of rotation. Okay. There actually our discussion was moment of inertia. But anyhow, I told you at the time, and while the starting of this chapter also I told you, in case of regular bodies, right, the geometric center coincides with center of mass, and it is also easy to identify the position of center of mass in case of regular bodies, right. Since the center of mass of the rolling disk is at its geometric center C, VCM is the velocity of C. It is parallel to the level surface. See here, which is parallel, no? So this is the level surface. So this is parallel to the level surface. The rotational motion of the disk is about its symmetry axis. The rotational motion of the disk is about its symmetry axis, which passes through C. Thus, the velocity of any point of the disk like P0, P1, P2. Thus, the velocity of any point of the disk like P0, P1, P2 consists of two parts. One is the translational velocity VCM and the other is the linear velocity VR on account of rotation. This is VR, which is VR, and which is the translational, that is VCM. So the resultant of these two is V2. So V2 is the resultant velocity of VR and VCM. VCM is the translational velocity and VR is the linear velocity. Okay, right. And if you go to the magnitude, the magnitude of VR is R omega, where omega is the angular velocity of the rotation of the disk about the axis and R is the distance of the point from the axis. Okay, where omega is the angular velocity of the rotation, of the disk. Okay, see here ma, omega is the angular velocity of the disk about the axis and R is the distance of the point, from the axis, or small r is the distance of the point from the axis. Okay, see this, that only he is saying VR is an account of rotation. The magnitude of VR is equal to R omega. Afterwards, omega is the angular velocity of the rotation of the disk about the axis and R is the distance of the point from the axis, that is from C. Okay, right. Next point, see this. The velocity VR is directed perpendicular to the radius vector. This is what? Perpendicular to the radius vector, right? The velocity VR is perpendicular to the radius vector. See here ma. After completion of that, he is saying this is what? The velocity VR is directed perpendicular to the radius vector of the given point with respect to C. And from this figure, you can also say that the velocity of the point P2, that is what? V2. The velocity of the point P2 and its components VR and VCM are shown. So here you can see ma, this is VR, this is VCM, this is V2. And VR is perpendicular to CP2. It is C, it is P2, and this VR is perpendicular. This is what? 90 degrees angle ma. So if you see clearly, you can observe, right? VR is perpendicular to the, okay, VR is perpendicular to the CP2. This is CP2 ma. It is CP2, it is VR, so which is perpendicular to the CP2, and it is easy to show that VZ is perpendicular to the line PO P2, I mean P0 P2. This is P0 and it is P2, right? This is P0 and this is P2. It is easy to show that VZ, okay, that is what here, you know, VZ here, that is what? V2, okay. V2 is perpendicular to the line P2 and PO. This is P2 and PO ma. So you can easy to show that is what? V2. V2 is perpendicular to the line PO P2. Okay, it is not VZ, it is V2. See here ma. So it is easy to show that. Okay, it is easy. You can easily show that V2 is perpendicular to the line PO P2. This is the line ma, this is perpendicular to the PO and P2. Now what I am saying is, therefore the line passing through P0 or PO, whatever it may be. So the line passing through PO or P0 and parallel to omega is called the instantaneous axis of rotation. The instantaneous axis of rotation, right? So this is what? Instantaneous axis of rotation. See here. And now at P0, the linear velocity VR due to rotation is directed exactly opposite to the translational velocity VCM. See here, this is VCM, no? Right? It is what? VCM. But he is saying that at P0, the linear velocity VR due to rotation is directed exactly opposite to the translational velocity VCM at this point. Next, further, the magnitude of VR here is R omega, where R is the radius of the disk, that's we know, and omega is the angular velocity. Okay, the condition that P0 is instantaneously at rest requires VCM is equal to R omega. So what we told, before starting of this topic rolling motion, I told you regarding the pure rolling motion, we have to see at any instant of time the bottom of the disc which is in contact with the surface is at rest on the surface. So to satisfy this, V maximum should be equal to R omega. Thus for the disc, the condition for rolling without slipping, you can also write omega is equal to V by R and alpha is equal to A by R, right? A is equal to R alpha, no? When V is equal to R omega, you can say that A is equal to R alpha, right? Which relates, that is what translational and it is what angular, right? Next, incidentally, this means that the velocity of point P1, is at the top of the disc has a magnitude of VCM plus R omega, VCM plus R omega, R ORR, it is 2 VCM and is directed parallel to the level surface, and this condition, that is what we have here, this condition you can also apply to all rolling bodies, okay, right. So in this class we discussed law of conservation of angular momentum and applications to daily life. So regarding this law of conservation of angular momentum, we discussed the applications due to the applications in daily life. This is the one example we consider to discuss, and then the skating, right, and the dancing, and that is what classical dance, right. So this will become the examples of law of conservation of angular momentum in our daily life. Thereafter we discussed rolling motion. So what is the rolling motion and what is the pure rolling motion and how to calculate, I mean what is the velocity of a body at point P0, at point P1 in case of rolling motion, and what is the condition for rolling without slipping, and what happens to the velocity at P1 when compared to the P0. These are all we discussed, okay, right. In our next class we will continue with next continuation topic. Thank you.